Hello everyone. Welcome to the session 11 of the for the problem solving session of the for the course Ultrafast Laser Spectroscopy. It has been last 10 weeks since we are discussing these problems which are related to the each week's modules which have been given. As usual, this week also we'll be discussing some of the problems that are related to the assignment questions, and thus we'll solve them. Basically, initially, since it's 3 and no one has joined yet, so we'll be waiting for a time for some time so that some people join, and then we'll continue the problem solving. Yeah, so now we'll be starting the session, and I'll be sharing my screen first. So, okay. So, first of all, I'll give a brief introduction to what we are doing now. So, first, since in the as a part of the session in this week, we'll be discussing the questions which were given questions related to which were given in the assignment 11. And now, without any delay, we'll be going on to the question number 1. So the question number 1 says, of the following one is or are not the magic numbers for the atoms to form nanoclusters, is or are. So first of all, wait a second. So what are they asking about? What the first is nanoclusters. Mhm. So what are nanoclusters? So far, whatever we have learned was of related to the nanoparticles. Okay. So what were nanoparticles? Nanoparticles were some like if you there are two techniques. First of all, in order to prepare the thing nanoparticles, we can go to the top down or the bottom up technique. Okay. Either from the larger or the bulk solid, you can break it further to give the particles that is the top down technique. And the second is say from the atomic level you can go through or say the molecular level you can come to a stage which is the nanoparticle stage. Okay. And how are these nanoparticles? Nanoparticles are say the combination of few atoms of some material which have a diameter that is in the range of nanometer. And in probably when you talk about atom, it is so that the atoms are in the range of angstrom. So when they combine together to form a unit, say 100 atoms or more, they can form, you can say, a nanoparticle. Okay, what they can form, 100 atoms can form a nanoparticle. But here there is a different term, that is the nanocluster. So what is a nanocluster? So cluster is smaller than nanoparticle. It is smaller than a nanoparticle. And how is it formed? So, similar to others, the nanocluster can also be formed when the few atoms they combine together, or from the nanoparticles they can further degrade or say etch to form a nanocluster. Okay, so this is what we have to just compromise with the handwriting, or I'll try to write in a better way. So, nanoclusters, what are they? Nanoclusters are, say, the further divided version of nanoparticles. And these nanoclusters, their size is in range of, you can even say they can be in the range of 2 to 3 nanometer in size, very small. And they can be formed by a combination of, say, 8 atoms or 5 atoms or up to 24, 25 to 100. Okay, so it can be more atoms also, but the diameter is less. So, and thus what they had asked is, the out of the following ones, which of the magic numbers the nanocluster forms. So, for the formation of nanoclusters, one needs to think that, based on the study, it is estimated that they are formed when certain number of atoms come together. Okay, and this number of atoms is fixed. And how much is it? See, this we can illustrate from the diagram. So this is a picture which I have taken from some source, and it shows that how the nano clusters can be in the range of, say, this is of 13 atoms, further from 19, 28, 32, 38, 44, and how they can go till 171. This is the largest one. Okay, and based on this, if you just use a logic, that is a simple logic, that they have given one number in the options, that is 2406. Okay, now if you just go on collecting, or if the gold atoms go on just collecting to form a nano cluster, if there are 2406 gold atoms, they somewhere come in the particle range. Okay, so they do not form a nano cluster, but then they become a nanoparticle. So basically, the answer to this question would be, the clusters can be formed in a number that is a magic number. And according to the studies or the paper which we have discussed in this week's module, there we can see that, further we'll be seeing that the 24, 55, and 140, these are some of the numbers in which the gold has formed nano clusters. And when it comes to 2406, that is somewhere in the range of nanoparticle and not a nano cluster. Okay, so um, overall in this question, what was the thing asked? But we have also discussed few extra things, that is, what is a nanoparticle? So nanoparticle is something, a particle from made from the atoms or molecules that lies in the range of nanometers. Okay, that can be a molecule also, and that can be an atom also. It is not necessary, but basically for nano clusters, here we what we discussed, that was only in the case of gold, although the nanoclusters can be of gold, silver, or copper. Some noble metals also, and basically it is not sure also, but they can be in any their oxidized state also, but they can be in the form of, say, atomic stage, or the copper zero oxidation state, or silver zero, or gold zero oxidation state. Now, coming to this, nanoparticles, they can be synthesized by two techniques. This I'll write it in a better way. That is the top-down technique, where from the bulk you further break it into further pieces so that it comes to a nano level, or the bottom-up technique. This is the bottom-up technique, where you can say from the atomic level, using by aggregation, they form the nanoparticle stage, and the size at the nano level is just restricted. They do not further aggregate to form a bulk. Okay, the diameter is in the range of nanometers. Okay, Then nanoclusters. Nanoclusters are smaller than nanoparticles, which can be formed when the nanoparticles are further degraded or etched to form a nanocluster. Basically, nanoclusters, their range, or if you talk about the number of atoms in a nanocluster, they can range from these so many examples we have taken from 13, 19, 28. Although what we had discussed that had 24 or 25 atoms, or say 55 atoms also. And further, when they reach to the range of 2400 or 2000 to 3000 atoms, then it comes to a nanoparticle level and not a nanocluster level. There is one more important fact about nanoclusters that we need to discuss is nanoclusters, they cannot be stabilized on its own. Nanoclusters need a core. Okay. Need a say a protein or a unit to stabilize them. They cannot be stabilized on their own. So you use a no so in the practically, in order to synthesize, you use lots of ligands which can stabilize them, and one of them is, say, glutathione, which is used for the stability. Then, for the formation of the nanocluster, it is estimated that certain numbers of them combine, and this number in which they combine, this is called as the magic number. Okay. So they had asked us what are the magic numbers in which the nanocluster can form in the atomic level. So nanoclusters can be formed in 13, 19, 28. So based on this and the observations or the examples which we discussed in the theory in the class, the answer was that if the atoms, they are in the number of, say, 24, say 55, or say 140, they are in the form of nanoclusters. But you, if the count is increased to thousands of them, then they come in the range of nanoparticles and not nanoclusters. Okay. So if any one of you have any doubt in this question, you can please ask, or else we'll proceed to the next question. Moreover, there is one more thing to discuss: in which geometry do they combine. So that thing we'll be discussing in the next question. But for now, I would say that they have a specific geometry based on the all the data which is collected through the various experiments done by various groups across the world. It has like they have an icosahedron sort of geometry, and which we'll be discussing in the next further coming questions. Now, if you have any doubt, please ask, or else we'll go to the next question. That is, yeah. See, here also there I have just given this graph which we had discussed in the in the week 11 videos. They see, this is a study of some group which where they have given that, see, this is a normal absorption spectra of each. For the gold cluster of 25 atoms, then 55, then 140, then 2406. See, this 2406 gives this surface plasmon peak, while the others, one for, say, 140 or 55, in each of these three cases, the surface plasmon peak has totally disappeared. So surface plasmon peak you do not get for the nanoclusters, but you get for the nanoparticles. Okay. So surface. So this is one more fact to be discussed, and that is the difference between the two: surface plasmon peak for nanoparticle and no surface plasmon peak for nanoparticle. cluster. Okay. Now, also, the nanoparticles, they give a weak emission, while this is the second one. This is also for, they give weak emission, while for the nanoclusters their emission is quite high compared to nanoparticles. Okay. Then yeah, what is the reason of emission? The emission is based on, say, some observe. This is simply a representation of how the emission can occur. First, it absorbs in the, say, in the UV range, and then it emits in two ranges. The first is the, from the excited state, it reaches directly to the ground state. Then from the second excited state, it comes to the first excited state, and then it emits. This can be second sort of emission. From second to first excited state, it comes through a non-radiative path. Then after, there can be another sort of emission, that is the infrared emission, that is from the, say, the surface states. Okay. So now we'll go to the next question, which is the two photon absorption cross section for gold nanoclusters and nanoparticles is. Okay. So increases with increase in the size of nanocluster, decreases with increase in the size of nanocluster, has similar slopes for nanocluster and nanoparticle, increases with the increase in the size of nanoparticles. Okay. So first of all, here see, yeah. So what is this two photon absorption process? And okay. So two photon absorptions means that, say, the property of nanocluster is two photon absorption followed by emission. Say you this is the ground state, okay, and this is the excited state. The energy difference between them is in the terms of wavelength. We'll call it to be lambda by 2. So what they do is, uh, yeah, or say it is new. So what they do is, first, they as similar to the further earlier sessions where we had studied the two photon absorption, they absorb a higher wavelength, or they absorb two photons of higher wavelength and emit a single photon of lower wavelength and higher energy. So here in this case, you will observe that, see, the two photon absorption, when you talk about, say, in here is a study that was done by one group, where they have given how with the size of the gold nano clusters, say 25 to 140, 3 to 309 number of gold atoms in the nano cluster, how with the since the number of atoms are increasing, the cluster diameter is increasing from 1 to 2 and 2 to 3, and how the with the cluster diameter increasing to, say, some level, with the cluster diameter increasing, the value of delta, or the two photon absorption cross section, which is denoted by delta, is increasing linearly. Okay. So there is a linear relationship in case of gold nano clusters between the diameter size of the cluster and the two photon absorption cross section. Okay. And what is this GM? This GM is the unit for two photon absorption cross section, which was given after the name of the Maria Gilbert Mayer, and it is equal to the 10 to the power minus 15 centimeter to the power 4 second photon inverse. The cluster diameter, what they are talking about, is in the range of nanometer. So basically, for this cluster, that the diameter is in the range of say 1.3. For the other one, it is 1.6, and for this, it is say 2.2 or 2.1. Further, for the nanoparticle range, if you study in the nanoparticle range, you will note that, see here, 375 or say 675 to 2406. This comes in the range of nanoparticle. Here also the same case happens. That is, when the cluster diameter increases or when the particle diameter increases in say from the range of 3.1 nanometer to say 4 nanometer, you will see that the value of delta, that is two photon absorption cross section, is also increasing. So this is similar in both the cases, where with the there is a linear relationship between the diameter or the size, and the second thing is the two photon absorption cross section. As you increase the diameter or size of the nanocluster or the particle, in both the cases the cross section or the delta value is increasing. Okay, now here in the second figure you will see that why is this decrease happening. So this is the value of delta upon n. Now, as you can see, the n is increasing in each case from red to green to blue. So, it is obvious that as the value of n will increase, the value of delta by n will decrease. And thus, you will see again there is a relationship, that is, as the value of or as the diameter, cluster diameter is increasing with the n, the value of delta by n, say the number of atoms, will decrease linearly. Similarly, for the other case, see here the value is not that changed because the value of n is has grown quite significantly. Okay, now we'll come to how now we have understood the topic, or we have given it a relevant reason from the observation. Now we'll come to the answer of what can be the answer to this question. So first they had asked two photon absorption cross section for gold nanoclusters and nanoparticles. What it does. So for nanoclusters and nanoparticles, both they have asked, and for from this graph we got to know that, see, from gold to, as the number of atoms are increasing from 25 to 140 to 309, you will get that there is an increase in the value of delta with the value of cluster diameter. So increase in the size increases with increase in the size of nanoclusters. Then second is decreases with the increase in size of nanocluster. So this is true for delta by m, sorry, delta by n, but not simply delta. So this is not the right answer. This is the right answer. And since we can see this is a multiple selective question, we have to look over the other two options that are also given to us. this third option has similar slopes for nanocluster and nanoparticle. So if you see the graph carefully, you will see that the slopes are different. They are not the same slopes. So we cannot say that they have a similar slope. So this is also not a right answer. Then we look to the fourth option, that is increases with increase in the size of nanoparticles. So yeah, for this case also, with increase in the size of nanoparticles, the value of 2 photon absorption cross section is increasing. So now we have come to the answer, that is, with the increase in size of nanocluster or nanoparticle, there is increase in the 2 photon absorption cross section. Okay, now I'll just give a quick explanation to whatever I had explained in this question. Wait for a second. Yeah. So, first of all, what is 2 photon absorption cross section? So, for the nanoclusters and nanoparticles, there is a fact, or there is an observation that these nanoclusters, they show this 2 photon absorption. Okay, what they do is they absorb in higher, they absorb somewhere, say if they absorb in a range of 1200 nanometer, so they absorb 2 photons of 1200 nanometer, and then they emit further in the range of 600 to 700 nanometer. That is it. Okay, just half of it. This is the fact, or this is the thing, that say they absorb 2 photons of this much wavelength, and they emit 1 photon of this. So this is the characteristic, or this is the property that is shown by gold nanoclusters, that is the 2 photon absorption, which we have also studied in the earlier modules. And what, based on how the size, how with the size this changes. So actually the thing is, in case of nanocluster and nanoparticles both only, with the change in size you will see a lot of variation in the absorption and emission. It does not remain constant. You as the diameter increases, they'll give you a mathematical relation based on the radius of the cluster or the particle, how the band gap is changing, therefore the absorption and emission would be altered. Okay, so here we discuss, there is simple observation where with the number of atoms increasing in the gold nano cluster from 25 to in the range of hundreds or in the range of 300, so they have taken quite a difference between each of the each of the readings which they had taken. They could see that as you increase the number of atoms a per cluster, or you say the diameter increase, the value of delta, it shifts. The value of delta, or the 2 photon absorption cross section, increases. Okay. The second thing is, in case of nanoparticles also, the similar observation is seen, that as the diameter will increase, as the diameter will increase, there will be the 2 photon absorption cross section will increase, although the two have a different slope, but still they have a similar trend. Okay, and the second thing is, if they had calculated, we would have calculated the delta per gold atom, or say the delta by n. Then in that case, as the number of atoms will increase, the delta by n value will reduce, and therefore you see that with the cluster diameter increasing, the delta by n value decreases. So here you get a simple slope, which is denoted by a red line for nanocluster and blue line for the nanoparticle. Okay, the value of GM was again was given by the Maria Zippert Mayer, who received the Nobel Prize in year 1963. Okay, one GM related to this international notations, that is the centimeter to the power 4 second photon inverse. This is the unit. In short, it is written in the form of GM. Okay. Now, if you have any doubt in this question, just ask, because this this is an important topic to discuss about nanoclusters and their size dependence on the absorption and emission. Okay, so the now the next thing which we'll be discussing will be the further observation of the nanoparticles. But still, if we'll go, if some few have any doubt, we can discuss. The next is, yeah. Okay, so here we have just one slide as the observation. See, this is for the gold nanocluster that is of 25 atoms. The absorbance is, say, in this range. Okay, and you will see that uh, the at 1290 nanometer it absorbs somewhere, and it emits, the emission is the two photon excited emission is somewhere here, say, which is in the range or centered at, which is in the range of, say, 800 nanometer. Okay, and when they plotted the log of the fluorescence intensity counts versus the power, they could get the value of slope, which was 2, which further confirmed that yes, 2 photon absorption is taking place. Then this is of the another example where gold particles, they have a diameter of 4 nanometer, and in this case also they see on the excitation using 800 nanometer, they see the emission that is in the range. And similar to this, when they plotted the graph, they could get that the value of the slope is 1.94, which is somewhere similar to 2, and this is case of nanoparticles. Okay, so we'll go to the next question now. The transient absorption experiments on metal nanoclusters reveal charge transfer constant of. Okay, so these are the nano clusters they had considered of 25, 55, and 140 nanometer, and in each case they had noted the, say, the time constant that was of 550 femtosecond. Now, when the decay study of each was done with respect to at different wavelengths, say 640 nanometer, they could see that there are two types of emission occurring. The first one had had a lifetime or the decay time of 1 picosecond. The second one had a decay time of, say, the second one had a decay time of less than 1 nanoseconds. Now, the homo-lumo charge transfer, what is it? So, nanoclusters, they have, see, from, you have come from the atomic level to somewhere which is close to the atomic level. So, basically, here also you can say that you can divide it into various, you can describe the nanoclusters in type of various energy levels. Okay, and in each level is separated by, each level is or has certain band gap or has certain energy gap from the subsequent further layer level. Now, in each case, when you say this is the highest occupied all highest occupied molecular orbital, and this is the LUMO. So when it absorbs certain range, the first absorption would be this, where the molecule reaches from HOMO to LUMO. So this is HOMO to LUMO charge transfer, and this charge transfer takes place in a very short period of time, that is of 1 picosecond. Okay, so this, say, this is the collection of atoms. and they form, say, this kind of icosahedral structure. Yeah. And the level, say, HOMO and LUMO for this cluster is, say, it has a band gap of some value of 1 to 2 uh, electron volt or somewhere. So this HOMO to LUMO energy band gap, for which it absorbs in the transient absorption, and this whole has a time of 1 picosecond. But in the second case, what is that they have written is core to shell. What are these core to shell? Okay, so this is taken as the core. Okay, this is taken as the core. And as I said earlier, the clusters are stabilized by some ligands. Okay, so the clusters are stabilized by some ligands, and these ligands are then, say, uh, help, or these also take part in the charge transfer. Okay, so these are referred to as shell. So the second kind of charge transfer that can be observed is from core to shell. Okay, from the core, say, the gold 27 or 25 atoms cores, to the shell, or say the ligand which is stabilizing them. For each one, because this is more prone, more probable, so it has a higher rate constant, therefore a lower lifetime or time constant, which is in the range of 1 picosecond. Okay, so for this, the answer would be 1 picosecond for HOMO to LUMO. Okay. Now, for core shell also they have given options. So for core shell also we can see what can be the option for the core shell. For core shell, it is in the range of 1 nanoseconds or less than 1 nanosecond. So this will be the option. The other two options are not right. These two options are correct. So these transient absorption studies, when they are done, you get a lot of bands. Okay, not even a single band, and for the each band it corresponds to, say, different energy levels and transition to different energy levels. Okay, and say, these energy levels, they are divided, say, 1s for H, 1p for H. And what are these H? And say here you write it as 1s for Pe, then 1p for E. Okay, this E stands for electron and this H stands for hole. Whenever the electron leaves the ground state and reaches to a higher energy state, then it is, then in this case, a hole is created in the ground state and the electron reaches to the higher state. And this is why you denote them as E and H and not anything else. In this transient absorption studies which were conducted in this experiment at 640 nanometer, they got two components. The first was the homolumo charge transfer component, which is denoted by red and had a lifetime of 1 picosecond. The second one was the core to shell, which was, again, it had a lifetime of 1 nanosecond and not more. Okay. Then if you have any doubt in the question, or else we'll go to the next question. Also, from this transient absorption study of various nanoclusters, you will see that the a delta is maximum for the gold nanocluster with the highest number of atoms, that is 140, and this peak is slowly Not increasing. The 25 and 55. 25 has a higher value than 55. Okay, now we'll go to the next question. Question number 4. The question number 4 asks, which of the following transition refers to band edge transition in the absorption spectrum of semiconductor crystals? Okay, so first of all, let's quickly see what are they talking about. See here, although the things are a bit blurry, but I'll just write them in fair so that it is more clear. This stands for, this stands for, this is 1 S 3 by 2 H. Similarly, the lower one is 1 P 3 by 2 of H. Similarly, this is 2S 3 by 2 of H. This is 1 P 1 by whole. This is 1S 1 by 2, I think. Yeah, of H, and this is 2P 3 by 2. Okay. And here the higher are 1S for electron, 1P for electron, and 1D for the electron. Okay. Now, in the nanoclusters, they have divided these as the energy levels. And in these energy levels, see, this is the highest occupied molecular orbital and this is the LUMO. So the first transfer is from say 1s 3 by 2 to 1s of electron. Further, the first to the third, then second to the second, and so on. So there are different kinds of transition that can be possible or that are possible. In the case of CDSE nanocrystals, CD cadmium selenide. So in each case, see their absorption peaks. In the absorption spectra, you will see the absorbance that happens, and this is the in terms of electron volt they have given the energies. Normally in the absorption spectra, what you study is the nanometer. Although that is also you can convert it in the electron volts or in the terms of energy, but in this case they have given the absorbance, and each peak they have given that each peak corresponds to which kind of transition they have given. Now it's quite easy to understand from the figure that this is the lowest energy transition. Okay, and therefore this would have the lowest energy and highest wavelength. Also, say if you talk in the terms of band, so this is the lowest band or the HOMO and this is the LUMO. And in this case, from the energy level diagram, if you see that the 1s 3 by 2 H has the highest occupied molecular orbital, while the this is the highest occupied lowest occupied molecular orbital, and thus since these are at the band edges, you can see, you can tell that the transition from this ground state to the excited state, this is called the band edge absorption. Okay, and as you go say from this 1 SE 3 by 2 H to 1 2 SE 3 by 2, sorry, yeah, from 2 SE 3 by 2 H you go to 1 S, this one. This is further with some high energy absorption. Then the third one corresponds to this 1 P 3 by 2 to 1PE. This is the third. So this is the first one. This is the second one. This is the third one. Then the fourth one is 1SE, 3S 3 by 2 H. Yeah, this one. 2 uh 1SE. Yeah, this one. Okay. So this is also the third one, and the rest all are also of low energy, high energy, low wavelength transitions. Okay. So yeah, which of the following transition refers to the band edge transition in the absorption spectrum of the semiconductor nanocrystals? The first option they have given is 1SE to 1SH, 1SE to 1S3 by 2H, 1S3 by 2E to 1SH, and 1S3 by 2E to 1S3 by 2H. So here, first of all, the transition or the absorption is one hint to this question is, see, from the ground state, or this is majorly referred to as the low energies are for the hole to hole transition, but the lower energies are normally denoted by H, which stands for holes, and the higher energy levels stands are denoted by E, which are given by, say, this. Okay, then in each of the cases, when you just divide them according to the energy gap and the between the levels, energy levels, and you see the 1s 3 by 2 has the highest energy, while 1s 1 by 2h has, and 2p 1 by 2h has the lowest energy. And this energy is becomes more negative as you go till the lower levels. Meanwhile, as you go from 1s to 1p to 1de, here it is not clear, but I'll just write it: 1s 1p e and 1se. In each of these cases, say from down to up, the energy is increasing. In all of these, the most fundamental transition, or the transition or the absorption that happens, or is also called the band edge absorption, is from the highest occupied molecular orbital, or the HOMO, to the LUMO, and which is given by, say here it is 1s3 by 2e, and it goes to 1se. Okay, if you would not have this diagram, this problem would not be very clear. But actually, this whole nomenclature for the each level is based on the spin angular momentum, and the spin momentum, and the angular momentum S and L values, and based on this they have we have divided them, or we have named them. So the answer is, okay, actually the arrows here are different. Yeah, the direction of arrow should be in this. From hole to E, they can go, and you can say that the one is 3 by 2 H to 1 is E. Okay, so the answer is 1 is 3 by 2 to 1 is E. So this would be the answer, but the direction of arrow is 0. Transition mainly in the absorption occurs from 1 is 3 by 2 H to 1 is E. Okay. Uh, so so far, if to make it more clear, I'll just rub these extra points on the overwritings which we have done. So this is the first, this is the second, and this is the third. Okay. The second, the transition also we have noted, and how the absorption happens to be, or we see in the absorption spectra or the transient absorption spectra. Okay. Now, if you have any doubt, feel free to ask, or else we'll go to the next question. Okay, so we'll go to the question number 5. In the experiment of Rosenthal and co-workers, the first lifetime component tau 1 in CDAC nanoparticle increases with, the answer or the options are: increases with increase in the size of nanoparticle, decreases with increase in the size of nanoparticle, independent of the size of nanoparticle, reaches saturation after initial increase in size, with size. So, what this TRPL stands? This TRPL stands for time resolved photoluminescence. Okay, so CDAC, cadmium selenide nanoparticles, for them, say, see this here. In this experiment, this was the experiment conducted by Rosenthal and the group, and what they had seen is, um, see here, this is the absorption spectra with the solid line, and the absorption is in the, say, in the 500 nanometer range. Okay, then in the same, the fluorescence is detected in the same region. Okay, when they did the time resolved study for that, and that too depending on the particle size, say the particle size for the nanoparticle size for CDAC is going from 25 to 29 angstrom to 31 angstrom to 35 angstrom, 44 angstrom, and 60 angstrom. Okay, you will see there is a fast decay in the smaller one. Okay, but as you see, their decay becomes slower when the particle size increases. And similar to this, the absorption happens to be, say, when the particle size changes from, the absorbance is noted at 515 to 627 nanometer. So this happens when the, see, from 25 to 29 to 60. In each case, as the diameter or as the size is increasing, the absorbance becomes more red shifted with increase in size. Okay. Now see, the diameter is increasing from 25 to 29 to 31 to 35 to 44 and to 60 nanometer. Okay. In this first case, uh, each of these functions, they, what they got was a bi-exponential function which had two values of tau 1 and tau 2. This tau is the time constant. This is 1, this is 1, and this is 2, tau 2. And this is the amplitude. Okay. you will see that when the particle size is increasing, say from 25 to 60, then 3.0 to 4.6, the first lifetime is increasing. Okay, the first lifetime is increasing, and since we have also studied earlier also that the time constant is inversely proportional to rate constant, right? Now, if you just look carefully at the amplitudes for the tau 1, you will see that the value of amplitude is decreasing. Okay, so time constant for CDSE nanoparticles increases with increase in size. So, this is the point to note. Time constant increases, that is the tau 1 increases with increase in the size. The second is amplitude, it decreases with increase in size. Okay, here what they have asked. Here they have asked, in the experiment of Rosenthal and co-workers, the first lifetime component in the CDAC nanoparticles increases with the increase in the size of nanoparticles, decreases with increase in the size of nanoparticles, independent of the size of nanoparticle, reaches saturation after initial increase in size. So first is that the increases with increase in the size of nanoparticle, it it is shown here. It is clearly depicted from this table and from this observation. Okay. As you can also see the lifetime or the time constant tau 1 is increasing from the figures also. So increases with increase in the size of nanoparticle. Then the second option is decreases with increase in the size of nanoparticle. So yes, it decreases, it does not decrease. So this is not the right option. The third option is independent of the size. So far this option is also not correct. Then the fourth option is reaches saturation after initial increase in size. Okay. So here reaches to the saturation after initial increase. This also so far we have not observed. So yeah, these three options are incorrect. The right option is increases with increase in the size of nanoparticles. Okay. Quickly we'll see what we had seen in this question. For the CDSE nanoparticles, they had done the time resolved photoluminescence study. Time resolved refers to at the smaller time scale each they have taken how is the decay happening. Okay. So here they have taken like when they record the absorption and the fluorescence spectra for the CDSE nanoparticles, you see that the two are the mirror image. Okay, like the two are in the same range, or say like yeah, they are seen in the same range. Then with as a function of the particle size, when they plotted at the same wavelength of the excitation, and you see the fluorescence decay or the photoluminescence decay with the particle size, you they say that the decay takes more time, or the time constant for each decay that increases with the particle size increase. So here they have given the time result of spectra for each from 25 to 29 to 31 to 35 to 44 to 60. Okay. And for each diameter increasing, they say that see here the first lifetime tau 1 is increase. increasing, right? And tau 2 is also increasing, but the amplitude details for tau 2 are not given. Although, according to the amplitude studies, there is also clear cut decrease in the amplitude uh, based on the TRPL studies for CDSE nanoparticles. Okay. Now, actually, there can be different studies for the photoluminescence. The first one which they have done is the TRPL, time resolved photoluminescence, but TC based on TCSPC also they can also conduct and calculate the value of tau 1, tau 2, and tau 3, and there you not even a single one, you can get a variety of values of these. Okay, so in the Rosenthal the and co-workers experiment, the first lifetime component for CDSE shows an increase in the size of increase in the time constant with the increase in the size of nanoparticles. Okay. Also, there is one more relation that the time constant has an inverse relation with the rate constant. Okay. Now, we'll go on to the next question. Okay, in case you have doubt with this question, just ask. Next question is question number 6. The 0.73 picosecond component observed in the experiment of Weiss and co-workers is assigned to. Okay. So first, the options are phonon coupling, electron phonon coupling, electron relaxation, and hole relaxation. Okay. Now, see, in short, we'll just see what are the things associated when the molecule gets excited or when the system gets excited. Not a molecule, but the system gets excited. Say here I have noted that this is the ground state level. Okay, this is divided into further levels. Now this is the highest, this is the excited state. Okay, this is the band gap between the two levels, that is denoted by Eg, right? Now what is told is, now suppose there is a system which is in the ground state. Okay, now with time, if you just give it, supply it with some energy which is equal to the energy gap between the two, say the or higher than that, even higher than that, the electron will reach to certain higher level. Okay, creating a hole inside. Now suppose it has reached from here, it may be somewhere here. Okay, now also now when the two say electron and hole, uh, now the electron has to reach to certain release certain amount of energy and reach to the ground state. When this electron and hole, they recombine, they emit. Okay, right? Now it may so happen that the electron can be in the excited state only, roaming somewhere here, it may be trapped somewhere here and is unable to combine with hole. Then in that case, relaxation happens. and the relaxation may happen in different like the relaxation may happen so that the electron is trapped somewhere, so there may be a non-radiative relaxation of electron, there may be a non-radiative relaxation of hole, or it may so happen that the electron may transfer its excess energy to the lattice. Now see, this group had conducted the experiment, and where they had calculated they had got the value of various time constant, got various time constants based on the the first one is TRPL and the second one is TCSPC data. Okay, so they got six time constants, and each time constant may correspond to a transition. Okay, so that can be an electron relaxation, that can be a whole relaxation. Okay, so here what they did, they whatever time constant they got was 0.73 picosecond, 4.5 picosecond, 48 picosecond, 0.7012 and 46. These three are in the range of nanoseconds, these are three are in the range of picosecond. First of all, this kind of relaxation is quite high. And when they just plotted each, when they for each of the components, keeping the time constant keeping time constant, they noted the value of amplitude. Okay. So for the component say 1 which had 0.73 picoseconds lifetime, the component 1 which corresponds to time 1, what they did, what that the that kind of uh, relaxation or the transition happened to be in somewhere not in the visible range but in the IR range. Okay, and thus this is the low energy transition, and generally the low energy transitions are associated with holes and not with electrons since they are of the higher energy. So low energy transitions are associated to or associated with holes. Okay, and thus from this observation, where they had kept the time constants to be time to be constant and they measured the amplitude for each case, they could note that for the say the for the first component with a very short lifetime was that was of 0.73 picoseconds. For that, the only reason was the whole relaxation. Okay, now as I told, see, in a system, if there is one electron, there is one hole. The hole is in the ground level, the electron is in the excited state. Now electron plus hole, when they recombine, there is for sure guarantee that you will get an emission. Okay, but in case the two can don't combine, that is also a real time case that happens. There can be many non-radiative pathways associated. Okay, non-radiative pathways to degrade this energy or energy dissipation. energy dissipation. How can that happen? That can happen by, if the electrons are trapped, only the electrons are trapped. Okay. In case these electrons are trapped, they will degrade, or the energy loss happens non radiatively. Or else the same can happen with hole. So this can be called as the hole relaxation. Okay. Or then both can happen. The electron is also trapped, the hole is also trapped. So this is called the Auger recombination. Thus, from each of these components, they had denoted it with certain type, kind of transition that happens in the CDSC crystals. But for this case, they told that, yeah, yes, this kind of 0.73 picosecond type of transition that happens in very high range, or the IR range, higher range of wavelength, that is the IR range, and in this case it will be calculated as 0.73 picosecond, and they gave that term to the ultrafast hole relaxation. Okay. So the electron relaxation, basically this lies in higher energy. Okay. And lower lifetime, but the whole relaxation is generally lies in the that picosecond range. Okay. Now, if you have any doubt in this question, ask, or else we'll go to the next question. Yeah. Now, in the experiment of Weiss and co-workers, the wavelength at which contribution from both electrons and holes to the total relaxation is equal to. Okay. So, actually, for this whole thing to understand, we need to discuss a few new terms which they had brought into consideration. Okay. So, first of all, see, what they considered is, they brought a new term that was, say, eta. Okay. So, what is eta? Eta is the fraction of the total fraction of the total normalized amplitude for a given component Cn, for the compared to the total electron decay. So they denoted it with psi Ne. Okay, so for Cn component, what fraction of total amplitude is contributed? Okay. So the value for this would be chi Ne whole upon chi Ne plus chi NH. Okay. And also they told that this chi Ne and chi NH, their sum is equal. This eta Ne plus eta NH is equals to 1. Okay. Now see, in this experiment, what they considered is, first, in the visible range, the electron relaxation is maximum. Okay. So what they thought is, now in the visible range, no holes will contribute. Okay. Now, since no holes are contributing, the total A would be equal to chi NE, right? And then A in the visible range. Now, they also considered that in the total IR region, okay, in the total IR region, only chi NH will be there. No electron contribution will be there, okay. Now, see, uh, for a particular value or the component n component of relaxation, say the total value of A was given as a ANIR can be given by, in the ANIR they can, it can be given by, say, they wanted to find a time where both contribute 50 is to 50, like the contribution to the total absorbance is from both the side, from the electrons and from the holes. So they gave it to be as 0.5 chi Ne plus 0.5 chi Nh, right? Now, see, one thing they told that the chi Ne is equals to A in the visible. Okay. So here you can write that the ANIR is equals to 0.5 A, what is it? Visible plus 0.5 of chi NH, right? And then to calculate the value of chi NH, they deduced the relation ANIR minus 0.5 A visible whole upon 0.5 is equals to chi NH, and on multiplying by 2 to both the numerator and denominator, you get ANIR minus, sorry, 2 ANIR minus A visible whole upon whole upon 1 is equals to chi NH. Okay. So from this what you got is chi NH is equals to 2ANIR minus A visible. Got it? So this is the answer to this. Now, see, uh, yeah, in the from this total experiment, when they calculated, what they calculated is, based on this, they calculated the value of amplitudes and their ratio. Okay. So, based on this, they also calculated that the value of chi Ne is equals to the value of eta Ne is equals to A visible whole upon ANIR by 2. Okay. Now, since this is a bit congested, I'll just write it in fair. Uh, yeah. So see here, we got two values. Okay. The first one was the chi NH and the second one was chi NE. Okay. Now here we write the value of eta NE by calculation is equals to A visible, right? Because that we got upon A visible plus 2 ANIR minus A visible. Got it? And when you do, the two get cancelled and it becomes A visible upon 2 ANIR. Okay, is equals to eta NE. Now what they did, they using the time constants calculated the value of fraction, and this fraction gave the value that how many electrons are there and how many holes are there, which corresponds to that particular time constant value. And from this whole relation, they also calculated that the contribution at which both electrons and holes give equal part to the equal contribution to the total relaxation. So for this relation, they got that the total contribution or wavelength at which both contribute equally to the relaxation is at 1170 nanometer, and that happens to be in the NIR range and not in the visible range. Okay, so the fact so far is true that in the, say, in the visible range, yeah, in the visible range, electron relaxation is dominant. In the IR range, relaxation is dominant. Okay, so yeah, uh, with this, do you have any doubt in the question? Yeah. Is there any doubt? Okay, so we'll go on to the next question. Nanoclusters are also question it says gold nanoclusters are associated with. Okay. So first of all, nanoclusters we discussed have following properties. First, they have diameter in, say, 2 to 3 nanometer range. Okay, highly small. Second, made up of starting from 5 to say 100 atoms. Okay, the third is they have icosahedron geometry. Icosa. Okay, wait a second. They have icosahedron geometry, and this is for gold nanoclusters. Okay. Fourth, follow the magic number count for formation. Then uh, they fifth is they give photoluminescence stronger than nanoparticles. Okay, so they give photoluminescence which is stronger than that which is shown by the nanoparticles. And the sixth point is they do not show surface plasmon resonance as shown by nanoparticles. Okay. So as shown by nanoparticles, they do not show surface plasmon resonance. So first option is not correct. It is wrong. Okay. So this is not the right option. The second option, that they have certain icosahedron structure or arrangement of atoms, that is correct. So they have icosahedron arrangement of atoms. The second is they follow free electron model. So yes. Seventh, the the seventh is the conduction is explained by. So this is also a right option. The third is photoluminescence with very high quantum yield. But but the quantum yield in their case is not very high, uh, which unlike is observed in the normal cases. But in case of the nano clusters, the quantum yield is not that much high. Okay, so the quantum yield is not high, but they have an icosahedral arrangement, and yes, they are following, they are explained by the free electron model. Okay, now the nanoclusters, let's just take a revision of their properties. First, they have a size that is in the range of 2 to 3 and even more. 2 to 3 and more range. Then they are made up of the atoms which can range from say 5 to say hundreds of atoms. Here you can see it starts from 13 and it ends at 171. So far in this whole, this is the highest reading. Then the each one has an arrangement, that is the icosahedron arrangement. The icosahedron arrangement can be given by, say, this is the uh, yeah, say this is the square, so, or not this one, it can be a pentagon, and then you get a top. Okay, so yeah, this will be like, yeah, now it will be like, and here also you'll get, okay, I'll just draw the fair one. And so in the base also you will get such type of arrangement. Okay. Okay, so now we'll go on to the question number 8. Sorry, question number 9. The question number 9 says the 100 picosecond component in the gold 37 cluster is ascribed to. Okay, so first we'll have to see what this gold 37 timer or says. Okay, so see here, this starts from, say, the basic monomer unit is AU13, right? Now this dimerizes to get, say, this is one unit and this is one unit. So these can dimerize and one atom is reduced to give AU25 and not 26. Okay. This 26 further combines with one more icosahedron and then they'll give AU37 kind of. So two gold atoms will be removed and thus it gives AU37 kind of nanocluster. And it is a trimeric unit of trimer of AU13. Okay, not a dimer but a trimer of AU13. Okay. So basically, in order to study how the from the ground level to the excited state on the excitation, what are the changes happening and how the transition is happening from the level, they have given, see a simple diagram. Say from S0, using the pump light, it reaches to the excited state. Say this is using the 1200 nanometer of light, it reaches from S0 to S1. Okay. Then from S0 to S1, this is the pump light, right? Using 1200 nanometer. Then again, there is a probe light which through which it excites from this up further higher to 820 nanometer. Okay. Then now it has reached from S0 to SM. This SM is a further higher level. They have not given the name. It can be anything. Further, from the there it can happen so that, see, from the S1 there are two pathways. Using the energy profile, you can see from S1 there are two pathways. From S1 it can go to further this state, the singlet state with of lower energy, and this is denoted by the S1 star state. It can go to this state in this 100 picosecond. Okay. Or else it can go to further higher state by absorption, and then from this higher SN state it can go to two. It has two options. The first option is it can go to the S1 state, or this SN state, from this state it can return to the S1 star state in the fraction of 1 to 2 picosecond. So these two options, they are carried out simultaneously with, and they have almost same time for the relaxation. Basically from SN it can reach to S1 and it can reach to S1 star also. But there is one more option that it can reach from S1 to the S1 star. Okay. The only need for this is maybe it can excite to this level and from this pathway it can reach to this. Okay. Or else from here only by certain amount of excitation it can reach to this S1 star of lower energy. And this whole conversion takes a time of, say, yeah, and see, this is at lower energy, this is at higher energy. You say the activation energy or the gap is quite less, so this can occur fast. Although this change takes place and happens to be in the time of 100 picoseconds. Okay. So the what are the transitions? What are the transitions that are happening The first one is from S0 to S1. Second is from S1 to Sn. The third one is from Sn to S1. Fourth can also be from Sn to S1 star. The fifth one can be from S1 to S1 star. Okay. Now, this electron dynamics which was studied, the lifetime for each was given, and from say sixth one is from S1 star to S0. Okay. So these are the things that can happen, and from S1 star to S0 it can reach with the time of 28 nanoseconds. During these processes occurring, this process significantly its time is increased to 28 nanoseconds. Okay. Now, based on what, and see here, the three trimers are sorry, the single trimer, it in the time of 100 picoseconds it reaches from this S1 to this S1 star state. Okay. And this S1 to S1 star transition is something which they have asked for, and thus we can say that the 100 picosecond component is for the charge localization also, but with a time of 100 picoseconds. Okay. So Sn to S1 star is not the right option. This happens in 1 to 2 picoseconds only. So the answer to this would be S1 to S1 star, which happens to be in 100 picoseconds. But from S1 star to S0, it takes place in around 28 nanoseconds. Okay, quite a large time compared to the other two. Now, okay, so now we'll go on to the next question. The next question says size dependence of color of nanoparticles is observed when. Okay, so yeah, see, first of all, for the nanoparticles, each their when you study in the nanoparticle level, you will note that yeah, there are different energy levels. Okay. First thing. The second is in these different energy levels, when we consider bulk, then they are not discrete. Okay. But in the other case, what happens? The energy levels in this case are discrete in case of nanoparticles. Okay. Now, there is one equation to just calculate relation of size dependence with color. Okay. Now see, whole this size dependence or the color depends on band gap. And how is this band gap calculated? This band gap can be calculated by, say, the band gap Eg can be given by, or Eg effective can be given by Eg at infinity. What does this infinity mean? Infinity means that the rate constant has infinity means that the largest possible value, then plus h square pi square upon 2r square 1 upon me plus 1 upon mh minus, here this is separate thing, I'll just continue this equation here, minus 1.8 h square upon r square. Okay, here this is the radius, or the this r is the radius of cluster, and this r is, say, Bohr's radius. Now, the Bohr radius, when this Bohr radius of the exciton, okay, Bohr radius of the exciton, this r, Bohr radius of the exciton denoted by r, say this is exciton. How it is formed? Exciton is formed when one electron plus hole, they give one this high energy particle called as exciton, which then degrades its energy and in the form of light, and thus gives photoluminescence. Okay. So when the Bohr radius, from this equation, when the we get that when Bohr radius is comparable to radius of nanoparticle, that is denoted by r, then the size dependence happens. And how does it happen? See, as you increase the r, the band gap reduces. Since the band gap is reducing, you get that the emission or the absorption is more redshifted. Okay, as the size increases, the absorption or the band gap reduces. As the size increases, the band gap reduces, and you get a red emission, or the emission in the red end. Okay, or which is red shifted. Now, the from the following options, so what can be the right option to this? The Bohr radius of the exciton, when it becomes comparable with the radius of the nanoparticle, then in that case the size dependence will be observed. The second is, if these energy levels are discrete and we get when the band gap is quite clear, then also you will see that there you will be saying that there is some size relation, or there is a trend or the dependence with the size. Okay. Now, if you have any doubt, then please ask, or else we'll go to the next question. Yeah. So here, what is the question asked? The long lifetimes obtained for large semiconductor nanoparticles are rationalized by considering. Okay. So why are the long lifetimes? Long lifetimes means why is the tau value high? Okay. So uh, first here there was a calculation. Okay. Now what they with the size dependency, here the diameter, which is not very clear here, as the diameter was increasing, you could see that the time or the tau is increasing with the diameter. Okay, 1 2 3 4 5. Okay, in the case other case also it follows a similar trend. Okay, as the diameter increases, the longer lifetime. Okay, and when they calculated it in terms of the rate constant. What is rate constant? Rate constant is inverse of the time constant. Okay, and thus in this case, if the time constant value is quite high, for the rate constant you will get a slope like this. Okay, which we are clearly seeing in this case. Okay, and thus using this total equation and this graph, they introduced say the value of a function which it follows, which is a minus b by d plus c by d whole cube. Okay, and thus for the longer life time constant and the low rate constant, there are few factors on which that depends, that is a, b by d and c by d cube. Okay, now amongst this, if you say that these say when the value of d is the diameter, it reaches, yeah, sorry. So, yeah, as the value of D increases, okay, you will see that the value of these two reduce, and therefore, when the value of D reaches to infinity, when the value of D reaches to infinity, the value of a function of D is equals to A and therefore becomes constant. Okay. Or now, the two factors which on which this whole value depends is what they had calculated, and it came to be like b by d depends on the density of the trap states. Okay, density of the trap states, what is it now? See, if you consider a nano range particle, okay, in the nano range the surface area is high. Okay, and compared to that, the surface to volume ratio, it reduces. Okay, since surface to volume ratio reduces, the density of trap states also reduces. Okay, so basically And the second thing is the C by D cube. This is directly related to the oscillator strength. So there are two factors which are responsible, or based on which the longer lifetimes can be attained. And they are, first is the density of the trap states, since this whole depends on a function which is equal to a minus b by d plus c by d cube. Okay, so first is the density of the trap states, the second option is the oscillator strength. Okay, the longer lifetime, for that can also be considered. So intersystem crossing can also be the option, or can also be considered for a longer lifetime. Okay, because anyway, if the intersystem crossing happens, you get a longer lifetime for any kind of transition to happen. Okay, now we'll go on to the question number 12. The question number 12 says, in the Kharkiv, Politis and co-workers, what they proposed is, okay, so what they did is, in the CDSE nanoparticles, they found there are ultra long lived trap states. Okay, sorry, ultra long lived trap states. So the trap states are longer. Okay, and thus for them they proposed a concept that there can be more than one trap states. That is why they have a longer lifetime. Here also, as you can see from one, with the normalized PL, the decay continues to a longer lifetime, and that is 2.4 microseconds. That is quite a large time. And the reasons for that, they proposed is, there are more than one trap states involved. And the first reason is this, they propose that there can be more than one trap states. And the second reason they proposed is, the uh, trapping can be, the trapping is more efficient. And so far, what we discussed from that, what we could get is, trapping can cause the non-radiative decay. Okay, and thus, um, that can just cause increase the value of Kr, and also they can also cause like the long lived trap states, which have a time that is of order, say, that is of a time constant of a value 2.4 microseconds also, and it has not even ended at that time also. Okay, so the two ideas that were proposed by the group based on the CDSE nanoparticles were, that they can have ultra long trap states, and the reason for that can be, there can be, say, there can be more than one trap states for the electrons or the holes, or else the trapping can be in a very efficient way, that is leading to a longer lifetime. Okay, so these are the answers. Now, if you have any doubt in any of the questions, please ask, or else we'll go on to the next. Sorry, else we'll just end the session. So in this week, what we had discussed is, uh, in the nano clusters, what are they? Then, in the nanoclusters and nanoparticle range, the non-radiative relaxation, that is of not a bi-exponential function but has many factors or many processes going on with it, and which are kind of the transitions that can happen in the absorption by the nanocrystals. We also discussed the semiconductor nanocrystals of CDSE, cadmium selenide. Then there were different experiments that were conducted by different labs. So first is the this Rosenthal experiment, the second one which was conducted by Weiss and co-workers, where they had given different reasons and they had found that there are various time constants which they could get, that were these values. When for the each one they had plotted, they could get that this 0.3 picoseconds, 4.5 picoseconds, they could give a detailed explanation of maybe which transition this can be of. Okay. And through the non-radiative pathways, there can be many non-radiative pathways going on, which can be in the electron trapping, hole trapping, or other recombination. They also deduced a mathematical relation to calculate that if for a particular transition of a particular time constant, what can be the percentage of electrons and holes for them. And because since electron hole recombination gives rise to emission, uh, the other electrons and holes which are not participating in the radiative decay, they will surely participate in the non-radiative decay part. Then we also discussed about the nanocluster properties, how they are the upcoming in like they are the topic of till now they are also a topic of research. And how are they different from the nanoparticles, what are the properties, what are the characteristics that we observed in the case of clusters. So far in this module we discussed only about gold nanoclusters, but there are copper and silver nanoclusters as well. In the picosecond time scale, what are the various transitions that can happen in the gold 37 trimer. Then how the size dependence happens, and how that depends on the band gap, and how the absorption and emission is also affected by the size. Then the long lived states, how they are responsible, and what are the, based on that there was a mathematical function that could be deduced, which depends on the various factors. This was the last question. And what is the reason for the long lived trapped states? Okay. So with this, we just if you have any doubt, you can ask in the discussion forum also, or else if you have any doubt, we can discuss in the still in the next session. So for now, thank you so much for joining the session. And